So we started talking about the leverage points of climate change. And our conclusion was it's really easy to identify the leverage points, but it's hard to use the leverage points that we have. So that's exactly where a systems model comes into play. Let's look back at our model. The real dynamic that we're talking about is too much energy leading to too much heat. And the thing that's driving too much energy is too much greenhouse gas accumulation in the atmosphere. But let's get creative. Let's broaden our perspective a little bit. The energy leaving the system is only 1/2 of the stock and flow, right? What if we could actually block some of the energy from hitting us in the first place? If we could block enough of it, it's easy to see with our model that it could offset the increased energy being trapped by greenhouse gases. And what if we took the same approach with regard to the carbon in the atmosphere? Of course, we could produce less of it, but if that's too hard, if we have to charge our iPad and drive our cars everywhere every day, we could look for ways to take that carbon dioxide out of the atmosphere, create a new flow called anthropogenic carbon removal, and lower the greenhouse gas concentration that way. And in fact, that's just what proponents of geoengineering are suggesting we do. Their approach has been referred to as hacking the planet, and it consists of two main sets of strategies. The first is solar radiation management, and the second is called carbon dioxide removal. Let's start with solar radiation management. The idea of solar radiation management is to reduce the amount of energy that hits the Earth in the first place by reflecting some of that energy back out into space. This is where we find some of the goofier ideas out there. Giant sunshades, umbrellas that we assemble in space, clouds of mirrors floating around the Earth in orbit. More realistic proposals have to do with changing the characteristics of the atmosphere itself. That is, manipulation of the content of the atmosphere so that it's more reflective and therefore bounces more radiation back out into space. Could that work? Let's look at a historical example. In August of 1883, a volcano called Krakatoa, located in Indonesia, exploded. But this wasn't just your run-of-the-mill volcanic explosion, if there is such a thing as a run-of-the-mill volcanic eruption. This was a massive, massive volcanic event. The explosion was heard thousands of miles away. Cubic miles of rock were thrown into the air, and waves caused by the event went around the world. And according to the report of the Royal Society in the UK, it caused waves that were detected at recording stations off the coasts of England and France. But the effect that we care about here is the effect on the atmosphere. The same Royal Society observers, compiling a bunch of reports from around the globe, described the appearance of a sky haze, they called it, that spread throughout the tropics, and that by November of 1883 had reached the United States and Northern Europe. This haze, we now know, was fine particulate matter that was thrown up into the air by the volcano and suspended there. And it caused phenomena such as coronas, or rings that appear around the sun. It caused really intense sunsets, a perceived dimming of the moon, and even the disappearance to astronomers of some of the dimmer stars in the sky. This was worldwide for the next 2 or 3 years that we could see these effects as the material settled out. And that's all pretty spectacular. But what else happened? It's estimated that the material suspended in the atmosphere reflected so much solar radiation back out into space that the world was cooled by greater than 1 degree Celsius in the year following the eruption. And it turns out that global cooling following volcanic events is a pattern that repeats itself throughout history. This is the effect that geoengineers think that humans can replicate. Create a haze in the atmosphere by creating an artificial volcanic eruption. And one technique for doing this is to have airplanes spray a class of sulfur compounds known as sulfate aerosols into the stratosphere. Researchers estimate that this could be carried out for less than $1 billion and would have to be repeated every 4 years, but could reduce incoming solar radiation by up to a full percentage point. Other researchers have proposed that we can do cloud whitening. We use a fleet of ships that are self-propelled and solar-powered, and they pump water into the cumulus clouds above the world's oceans. By increasing the amount of water vapor, we make bigger, fluffier, whiter clouds, and more solar radiation reflected off the atmosphere. The second major technique, carbon dioxide removal, also has some more and less plausible variants. Ideally, we would just sweep carbon out of the atmosphere, right? We'd aim a vacuum at it, suck it up, pump it deep underground, store it in rock formations, and it couldn't do any harm to the atmosphere. Unfortunately, we don't possess the technology to do that. We can imagine some fanciful representations of it, like artificial trees sucking the carbon up out of the air, but why use fake trees when there are real trees, right? One way of combating climate change that's long been recognized is the reforestation of deforested land. Trees, growing and sequestering carbon into wood over hundreds of years are a great way to take carbon out of the atmosphere and store it long term. So, although reforestation contributes to a reduction in greenhouse gases, the real geoengineering story takes place in the oceans. Unlike trees, carbon is taken up in the oceans by algae, which have very short lifespans. When algae die, some of them sink to the floor of the ocean, and the carbon goes down there with them and becomes sequestered in the dark and cold of the deep ocean. It turns out that algae in the ocean are extremely nutrient limited, and in particular, algal growth is limited by iron. So, one geoengineering suggestion has been that we go dump some iron into the ocean, cause these great big blooms of algal growth, those algae then die and go down to the bottom of the ocean, and we increase the amount that's sequestered by this algal growth dropping down to cold, deep ocean process. Takes the carbon out of circulation.